Hey folks, thanks for being here today. I'm Nick. I lead the technical and product direction for the Truffle suite of tools. On the internet, you can find me as @Gnidden, or in the Netherlands, I believe it's pronounced Gnidden. Sorry, my jokes only get worse from here. So I'm going to be talking about Truffle Decoder, which is a library that we have for taking raw EVM data, like hexadecimal bytes, and converting them to high-level representations of actual like Solidity and ABI variables. So I'll start by talking about, why do we need another decoder? And then I'm going to just do a bunch of demos and then close up. Should be a good way to fill 20 minutes. I think so. So there are a number of decoders in existence today. I think probably the most popular is Ethers.js, just because everyone, Ethers in any front-end code, Ethers is under the hood. But for Truffle's purposes, and as we're finding out, for a lot of other tools' purposes, we need more detail than what Ethers can give us, or what Ethers, it's just not what Ethers targets, right? So firstly, Truffle really needs to support everything. And this motivation is perhaps a little bit outdated, right? Nowadays, all the decoders support nested structs, arrays, and everything. That wasn't always the case. But Truffle Decoder goes a little bit further than that. You'll see the last point there is we also want to be able to just decode storage variables, which I don't think there's a standalone library for doing that today. So yeah, we wanted Truffle Decoder to be complete, right? Decode any kind of thing, whether it's a call data, whether it's a revert message, whether it's a custom error, whether it's user-defined value types, right? Like all features, we want to be complete with our decoding. And we also don't want to lose type information, because I don't know if you know, but you could encode a hexadecimal string as UTF-8, and how do you know which it is? Or if you have an integer, how do you know if it's a uint128 or a uint64? And so, if you're trying to do machine processing of decoded values, you should have the type information alongside the values so that you know how to display it, right? Oh, you have a hexadecimal string, you should display it as a however you would display hexadecimal. Or you have a number, you should display it how you display a number, right? Beyond that, we want to use as much information as we can, right? The ABI is great, like props to the Solidity team for maintaining the ABI spec, but it is lacking in a number of areas, right? Like in Solidity, you can define a contract variable, or you can reference an interface. Well, in the ABI, those just become addresses. So if you're Truffle and you want to present information to developers, well, you probably want to be able to present information to developers that say this variable is this type of contract. Even better would be if you could say this variable is an interface, or is of type interface, but when it was instantiated, it was actually an instance of this contract, right? So we can do that kind of like inheritance figuring out. And then lastly, we want to not break when there's malformed data, right? So, you're dealing with the blockchain. Not everyone is running, like a Solidity compiler version that encodes things correctly in all situations. And so sometimes data is malformed. We chose to take the approach that if there's malformed data, we should show a detailed error message for only the part of the data that's bad, right? So if most of your transaction, right, if you're decoding some call data, right, and you have a struct, and one of the fields of the struct is malformed, but the rest of the struct is fine, well, we want to show the decoded value of the rest of the struct and then have a nice error message that says, oh, well, this array index is off by whatever, right? So effectively, this boils down to we wanted a machine-readable, like decoded data format that uses as much information as we can, right? If we have the source, use the source. If you only have the ABI, well, use only the ABI. And machine readable, like we often have to display blockchain data in all kinds of places, right? And so today, I think there's probably two main places where we're using Truffle Decoder that are worth calling out. One made a splash around the end of last year where we added some decoding views into MetaMask. And now when you go to confirm a transaction with MetaMask, you will see there's a data tab, and that data tab will go and it'll fetch the source code from Sourceify and or Etherscan. And it will run Truffle Decoder inside MetaMask to show you, what you're about to do. What are you about to sign? And this, having a machine-readable format for this is very valuable because it means that we can take this high-level representation of data and translate it into a body of React components. And what the MetaMask team has done is they see, it's an address, right? Because we include the type information. So we have our decoded value. There's an address somewhere in that decoded value. MetaMask goes and it looks up, do I know about that address? Oh, right, it's in the address book. Or, it's a token. And so there's a lot we could do there beyond just, the traditional Ethers style or, any of the other existing human readable decoders that just give you a string. We can say, it's an address. We know about that address. We can add context clues. And that's really just the beginning. I'll talk a little bit later on about where we're going with that, what we could do with this information. The other use case, this is hot off the press, is we just released a VS Code extension that has Truffle's debugger built into it. I'm not here to talk about that, but we use all this development-focused information from our decoded values to give context clues. Like in my screenshot here, you can see this is a contract, and it shows you the address. If you resolve this inside Solidity, you'll get an address. But we also know what type it is, so we know it's, in this instance, it's Magic Square. That's the name of the contract. So that's really powerful, and that can really help. A later iteration of the VS Code extension, you could imagine very powerful mouse overs. You mouse over a variable, you see exactly where it's defined. You can trace through the inheritance hierarchy. The C3 linearization stuff is good on you, Solidity, but it's chaos. All right. Anyway, enough about me talking. Let's look at how to actually use this thing. So I have maybe 4. We'll see how much time there is. But here's the basic process. I made some helper methods. So we have this get environment. All that does is it returns the provider and the Etherscan key, because most of the contracts that I'll be demoing don't have their source code on Sourceify. So we have to pull it from Etherscan. Bigger? Sir. Better? Cool. And then we're going to get the transaction info. This is just doing an eth-get transaction and eth-get transaction receipt. And we're also going and we're iterating through all the logs to get all the related addresses. And this is another thing that I'm not going to talk about, which is Truffle Fetch and Compile. Truffle Fetch and Compile is our library that just goes and it talks to Etherscan and Sourceify and it looks up addresses. And it returns this project info, which contains all the information that the decoder needs. We then go and initialize the decoder, given the project info and the provider. And then you can do actually decode transaction. And I'll show you the other methods that we support. And then we're just going to print it. So I'll show you that with the first demo. Somewhere in here, not that one. So I'm going to show you to start what I mean by machine readable. Oops. And we're just going to wait for the blockchain. Oh, here we go. Cool. So you can see that this is the decoded result. It's a transaction. It's a function call. It was the ENS registry with fallback contract. This is the ABI of the contract. And these are the arguments to the function call, right? So for each argument, well, you see there's a name and a value, but the actual value of that node first argument, well, you see here there's the embedded type information. So we know that the first argument is a bytes. It's a static bytes of length 32. And the value is represented as follows, right? And then, you see label is also a bytes 32, owner is an address, right? So everywhere in this decoding, you see what kind of data you're dealing with. And if you're imagining, well, how am I going to make a general purpose display of anything, right? You need this information, right? But maybe I'll switch. We have a nicer way of looking at this, so I'll show you the second example. It's the same transaction, but I'm just gonna, from here on out, I'll stop the JSON, and I'll show you, I'll use our inspector just so you can kind of see what is supported. So here, it's the same data, but we feed it through a console printer, basically. We'll just print it for you because, well, it's nicer to look at. So you can see that the transaction is a set subnode record call. Here are all the arguments. And in my demo, I'm going and actually decoding all the logs as well. Pretty cool, right? Let's get more complicated. So transactions are often not so simple as one function call. There's now this like multi-call standard, which allows you to pass an array of bytes, like an array of bytes arrays, where each of those bytes arrays is its own call data, like its own transaction. So we have the concept in Truffle Decoder of interpretations, and these right now are hard-coded, but the idea is the decoder will identify, once it's decoded, it'll be like, oh, are there any patterns I recognize? Aha, there's a multi-call pattern. So that means that I have to go through that array of bytes arrays, and I have to go and decode each one separately to present it nicely. And you'll see that once Infura gets back to me. Eventually. Everyone having fun? I could also skip over here to where I've already done all this. Yeah, so here is I feel like I'm on a baking show. I just took the result out of the oven. And you can see that this transaction was a multi-call. The multi-call is the contract name, and the function is aggregate. And we went and we decoded each of the things. This was just a random transaction I picked last night. And you can see it's a bunch of other function calls. So I could show you what it looks like, but basically in the decoding result, there's a field interpretations, and it says, oh, there's a multi-call interpretation if you want it. Right? So in addition to the raw decoding of, well, we called a function called aggregate, and it's an array of bytes. We said, and we suspect that array of bytes is a bunch of separate call data that we can decode. And so, whatever this person was doing with this transaction, they appear to be retrieving rewards. So you can see that it's pretty cool, right? And in our printer shows you the structs. So if you actually use the machine readable output here, you would be able to pinpoint exactly where that struct was defined. You could even go so far as to identify the line of source, like the source range where it was defined. So for development purposes, this can be very, very beneficial. But I mean, if you're looking at like the MetaMask use case, well, you don't really need to link to the source code in MetaMask, although maybe it'd be cool. So that's that one. Then I have one more demo, which is everyone likes decoding storage, or everyone wants to decode storage. So we do that. We'll try and do this for real. And then I'll show you the pre-baked one. Oh, before I do that, so I showed you the transaction decoding, but let me show you the storage decoding. So storage decoding, most of the people in this room probably know that mappings are non-enumerable. So how do you decode storage if you can't enumerate mappings? And so what we do is we expose this watch mapping key interface, which you basically just give it an expression. In my example, I just said, okay, I want to know the owners of NFT ID 0. I want to know the balances of, that's me, and I want to know the token URI for token ID 0. And so to invoke the decoder for doing storage variables, well, there's this decoder.variables method that just returns the variables as name-value pairs, where the values are that machine-readable format that I showed you. But before that, we do watch mapping keys. And so this tells the decoder that as it's going and decoding the state variables to go and get, to actually resolve all those mapping keys that we can't enumerate, the specific ones we're interested in. And so you can see here's this NFT. Let's see if IPFS resolves. Kind of. See if this one resolves. Nope. Well, IPFS, what can you do? But that's what's on the blockchain, at least. So you can see, and yeah, so we have the mappings, the specific ones we asked for. We asked for the owner of the token ID 0, and we asked for the, the balance of my account for this contract, and it resolves there. I didn't ask for token approvals or operator approvals, so that's why they're empty. So that's pretty much what I have to show you. I mean, if people have questions, once I wrap up, I can hack and show you anything you're interested in. But back to the slides. So there's some documentation. I'll just show you that quickly. This is our Truffle Decoding and Encoding docs. We really have 3 packages. Truffle Decoder is this like high-level interface that talks to the blockchain, does the get codes, the get storage ats. But all of the logic happens inside Truffle Codec. Truffle Codec makes no network connections. It has like no dependencies other than bn.js, basically. And so Truffle Decoder just invokes Truffle Codec, which has all the meat and potatoes logic. And then I'm not talking about Truffle Encoder today. But in Truffle Codec, you can see the format is documented here. And I kind of showed you in the terminal earlier what it looks like. But the format for the output is well documented. And there's types, addresses, etc. If you want to play with my demo, you can go to github.com/gnidin/decoder-demo, and here's all the scripts I just ran. You can play with them. The multi-call stuff's not merged, so number 2 will break. And if you're curious about fetch and compile, you can see the package on NPM. But what's next? Well, we want better pattern recognition. I was telling you about the multi-call interpretations idea. Well, we want to be able to interpret proxies, because right now, if you ask for the state variables for a proxy, you're probably only going to get one state variable called implementation. Well, Truffle Decoder should go and resolve the implementation, see what the state variables the implementation defines, and then go and decode those, right? So then beyond that, like, well, if you're, for whatever reason, ERC20 doesn't use fixed point numbers, it's all decimals, and then there's a field that represents decimal places. So we should go and see, oh, we're dealing with an address. That address appears to be an ERC20 token. Well, I better call the decimal places method, figure out how many decimal places there are, and then the decoder would produce better than just uints. It would produce decimal display numbers that people, you don't have to like count out 18 digits. And more things like better ENS support. If an address comes back in a result, we should automatically do a reverse lookup. Beyond all this like core decoder logic, we're also looking at actually building a library of React components. Like we have the ones in MetaMask that Truffle helped with, but we want to take that out of MetaMask, and we're thinking of calling the package like Truffle Codec components. Basically, it would have a body of React components, like a library of React components that you're dealing with some Truffle Decoder result. Well, you don't want to go and like type value if it's an address, display it this way. No, we want to provide those React components for you, so all you have to do is produce this decoding and then feed it to a dispatch React component, and voila, on screen your data looks nice. And then of course there's the case where there's no source code or ABI for private contracts or whatever. Well, there is 4byte.directory, right, where you can just look at the first 4 bytes of call data and see, well, that looks like a transfer function. And so we should use that information where it's applicable. There's more than this, but I appear to be out of time. I guess I have time for a couple questions if anyone's curious about anything.
So at the beginning you mentioned you would like to decode anything possible, and you also mentioned user-defined value types as an example. For user-defined value types, you probably need a kind of display function that is unique for each user-defined value type. For example, fixed point types, then you want to have the decimal point in the right place.
Yeah, we'd probably do that with interpretations. We do currently already support user-defined value types. We just don't do anything fancy on like a per type basis. But it will show you the name as defined in Solidity. Yeah, I should have put something together.
So, could there be some kind of custom hook mechanism or something like that is source code specific?
Yeah, well, that's what we're thinking with this like better pattern recognition, right? When you instantiate Truffle Decoder, you should be able to specify your like interpretation strategies,
cool.
Right? And that would be like, oh, well, I want Uniswap's multi-call. I want, Tornado Cache's user-defined value types to display this way, right? And so that would be this like caller responsibility to say how they want their data defined. And then Truffle Decoder would go and, anytime that kind of thing appears anywhere nested, right? Like maybe that user-defined value type is inside a struct. Well, that's what Truffle Decoder is good at, is like navigating its way through structs. So yeah, that's
Yeah.
kind of the path there.
Cool, thanks.
Mhm.